Okay, yeah, can you hear me now? Okay, so let's start. Okay, so let's start. So we have discussed the idea about conception about what is temperature. Now we will try to quantify and find the globally accepted scale for measuring temperature. So that will be our next topic. So temperature, what temperature tells you? Temperature tells you whether two systems are in thermal equilibrium with each other or not. So, and this conception of temperature we came from, it's coming from the zeroing law of thermodynamics that tells you that if some system are in thermal equilibrium with each other, then there must be some property of that system which are common to all of them, and that property we call it at temperature. And we saw that if we have a system, simple system, whose thermodynamic coordinates are x and y, determined by only two thermodynamic or microscopic variables, which are x and y. Empirical temperature is given by some function h of a, which is a function of x and y. Okay, so this relation actually gives you an idea of how you can measure temperature. So you can take any thermodynamic system which is sensitive to hot or cold, which is sensitive to temperature, which is sensitive to hot things or cold things, can be used to measure temperature. So how we can do that? We have already drawn the isotherms. For this particular system A, if we draw the variation of this thermodynamic coordinate x and y for different values of fixed temperature, then we will have lines like this, right? So these are called isotherms. We have already in the last session discussed, described, and defined what we call by isotherms. So these are isotherms. each of them corresponds to different temperature. Let us give them some name. So this is T1, T2, T3, T4, T5, T6, T7, T8. So these are different temperature, and for each temperature we have different isotopes. Now, what we can do, we can fix a particular thermodynamic coordinate. For example, y. We can fix y. I will give example and analogy to this just now, but let us try to understand the idea behind a thermometer or a temperature measuring instrument. As I told you, any system, any thermodynamic system which is sensitive to temperature can be used to measure temperature, can be used to measure temperature or compare the thermal equilibrium between two different systems. So how that can be used? So this is the diagram. This is the diagram where the two coordinate thermodynamic coordinate x and y, and these are isotopes. Each of these on each line, every step are in thermal equilibrium. But for example, if I take this particular line with temperature T3, each point on this line is specifying a particular state for the system A. And all these points, all these states on this line are in thermal equilibrium because they are characterized by this common value of this temperature T3. Okay? So now, if I fix one particular coordinate, let us assume that let us fix y coordinate of this system. I am keeping y coordinate same as this value. I am not changing. I am arranging the system in such a way, making apparatus in such a way that for this system A, this y coordinate will not change. Okay. And if I change the x coordinate, this will, this line, this constant y line will intersect all these isotopes. Now what will happen? If I keep this y coordinate same and take my system from T3 temperature, let us assume that if I keep my y coordinate fixed and my system is at T3 temperature or the isotope which corresponds to temperature T3, that means my system is in this particular point. Okay? Now if I increase the temperature from T3 to T4, what will happen? The system will go from this point to this point and keeping my y coordinate fixed, right? So there will be a change in x coordinate. So x coordinate was here, x coordinate was, now the x coordinate is this. There will be a change in x coordinate. I can measure the change in x coordinate, right? And that's why in that way I can measure the difference between these two temperatures T3 and T4. So this is the basic idea of the instrument called thermometers, how we measure temperature. So I will explain what we can do. As I told you, we can take anything. We can take any object which is sensitive to temperature, which is sensitive to hot and cold things, and use that object to measure temperature. For example, simplest example, let us take a metal meter stick. So this is a metal meter stick. So this is some metal stick. Let us assume that the length is 1 meter. Okay, at a given temperature, say at some given temperature, this is the length. Now, if I some cold temperature, let us assume that this is the length of this metal stick. Now, if I take this stick and put it in some, put it in contact with some hot object, then what will happen? The length of this stick will change, will increase. Right? So this could be used to measure temperature. So this will be my increment. So I have put it in a cold object and I obtain this length, and I have now putting it in, if you put it in a hot object and this length changes, then this will be the change in the length. So I can compare things using this meter scale. I can scale this increase into some arbitrary scale, whatever I want to do, whatever arbitrary scale I want to choose, and I can use that. I can put this meter stick into another object and find that that is expanded to this length. Then I can say that this particular object, say this is object A, this is some system A, this is some system B, and this is some system C. So I can compare these things. I can say that the increase in length for object C is in between the increase in length for object A and object B. So the temperature of this object C will be in between this object A and object B. And if I properly calibrate the increase, then I can in fact actually tell you what is the temperature of this object C. So I will come to the calibration. How we will calibrate these things? I will come to that. So this is basically the idea for thermometer. Simple, basic, simple idea for measuring temperature. How we can measure temperature? So any object, any system that behaves in a certain way when it comes in thermal contact with some thermodynamic system, that the behavior changes, then that can be used as a temperature. So this is a simple example. Okay, but there are some problems. So whenever we are defining some instrument, some units, then we should follow some universal convention. Because if we do not follow some universal convention, then we are all free to choose our own convention. As I told you that I can split this range into arbitrary number of divisions according to my convenience and make my thermometer. But the problem is that measurement will not be universal. If someone has a different instrument and measure the same temperature, then we will not, there will be difficulty to come to a same conclusion. So we should follow some universal convention. And I give you a simple example, but there are several problems associated with this example. Because this is not a good thermometer, because always along with this meter stick I should carry some other stick which are not sensitive to temperature. Otherwise I cannot compare the increase in length of this meter stick. Okay, so this is not a good example, good thing that can be used as a thermometer. So what we can do, we can take a good example. We know that liquid also increases volume if the temperature of the liquid increases. We can take liquids to measure temperature. Let us assume that we have this amount of liquid here. When it is placed on a cold object, and if it is placed on a hot object, then the volume of the liquid will increase, will surely increase. So this will come to somewhere here. So there will be, so this is the level of liquid when it is placed in a hot object, this is the level of liquid when it is placed in a cold object. So from this increase, I can calibrate this increase, and I can have my own thermometer, liquid thermometer. So, but so there are interesting ideas. So this increase is not, most of the time the increase in volume is so small that if you put this liquid in this kind of setup, then the increase will not be that much that you can see it in your naked eye. So people have interesting ideas that you have a small tube attached to a large container of liquid. So there are some liquid, large amount of liquid here, and there is a capillary tube here, very small tube. Then the volume, increase in volume, delta V, will be given by, so let us assume that if I increase the temperature of this liquid by delta T amount, then the increases volume is delta V, which will be, so let us assume that the area of this is A. Then the delta V will be A times delta X. So delta X is delta V by A. So delta X is the quantity, delta X is the quantity which we see in our eyes. So if I make this A smaller and smaller, my delta X will be bigger and bigger for same amount of delta V. So I will be able to more precisely observe what is the change in temperature. So this is the idea of your liquid thermometer. The thermometer you use, medically used thermometers. So there are some liquid, and now which liquid we should take? So there are different groups. You can take mercury. There are thermometers which are made of alcohols. So different liquids can be used to make this thermometer. Okay. Now I can calibrate. Now the next objective is to calibrate this thermometer. I can put this thermometer on a cold object and I will get a reading here, and I can put this thermometer on a hot object and I will get a reading here. Okay, so let us assume that this cold object reading I assign 0 and this hot object reading I assign 100, and in between this range I am dividing it into 100 equal levels. So that will be my calibration, and that is perfectly fine. That will be my arbitrary calibration of this thermometer, and that is perfectly fine. But the problem is, this thermometer cannot be used by others because it has been calibrated by me according to my convenience. Physically, everything is correct, but we should have some globally accepted calibration of this thermometer. So for that, actually, what I can do, I can choose this cold object as a mixture of ice and water. So this cold object would be a mixture of ice and water, and that will set by 0. And the hot object could be boiling water. Okay, so this could be the boiling water. And this could be a globally acceptable definition of 0 and 100 for this thermometer. So there are problems. I will come to the problem later slowly. But this could be. This is the definition which universally, people around the world can accept, because everyone has ice and water. Everyone can have boiling water, so they can calibrate their apparatus according to this arrangement. So this is a particular arrangement you can do. And for example, my favorite liquid is mercury and your favorite liquid is alcohol. So I can make a mercury thermometer, and you can make an alcohol thermometer and calibrate our both thermometer at 0 and 100. Then we can work. But the problem is, if we have two different kinds of thermometer, say this is my temperature, this is this is the height, and this is my temperature. Say for example, this is my temperature 0 and this is my temperature 100. This is the boiling point. My thermometer is here, and the boiling point of water thermometer. These 2 points have been calibrated for two different liquids. But the problem is we do not know what happened in between that. Either the expansion is linear or non-linear, whatever the expansion, we do not know. So you understand that at these two limits, where these 2 points, where the calibration has been done, we will be able to get correct reading. Okay. For example, I am assuming that this mercury thermometer is following this path. So this is how the length changes for mercury thermometer, and this is how the length changes for alcohol thermometer. Then if I take this thermometer and put it in some other thermodynamic system, and I find that this level of mercury comes from here to, for example, 3/4 of this length, then I will say that the reading of temperature is 75 in my thermometer. But it may happen that in some other liquid, when I put this thermometer into the same object, the reading comes not to the 3 foot but to some other values of this total. So that thermometer will give you different reading for the same thermodynamic system. So this is the first problem, because we do not know this behavior, how this liquid can. We need to find out. We need to find out the substance which has a linear behavior. So that will give me, that will give us a right choice for a thermometer substance. So this is the problem with liquid, and another problem is with this boiling, with the temperature, boiling temperature of water. As you know that this depends on several other factors. I am doing my experiment here. Someone may calibrate his thermometer at the top of some mountain. So we will find two different, our thermometer will be calibrated in two different environments. So this temperature, this boiling point will be different for us. But if we measure some physical quantity, for example, something physical, with those two thermometers, they will give different readings because initially they are calibrated differently in different environments. So these are the problems with this liquid thermometer. So these problems can be solved by gas thermometer. So I will come to that. What are the advantages? And gas thermometer will also tell us something more interesting about the temperature. So what is a gas thermometer? So as solid as liquid, gas also expand with temperature. Okay, so we can have a cylinder like this. A simple setup. We can have a cylinder like this. Some gas inside the cylinder with trapped through this piston, and some weights on the piston. Okay. Now I know what is the surface area of this cylinder. So my pressure will be simply, so let us assume that each of this ball has weight m. So mg, 3 mg divided by area plus the atmospheric pressure. So this is the pressure. The volume is given by, so let us assume that this is my height. So H times A. So this is the volume of this cylinder. Okay. So since this piston always has three masses here, so the pressure of this cylinder, the setup is such that the pressure cannot change. Okay. So now if I put this cylinder on inside, let us assume that put this cylinder V equal to HA, put this cylinder inside some ice water. I will have a reading for this H, so I can plot. So let us assume that this is my temperature axis and this is my H axis, this height axis, and this is my zero temperature, which is temperature corresponding to ice as I defined, and I have a reading here. And now if I put this into boiling water, which is according to my scale is 100, I will get some another height. For example, here. Okay, so I can now, so this is my scale. I can now divide this area between 0 and 100 into 100 times and have my thermometer. I can put this cylinder into any other object and I will get some reading, and calibrating this I can find out what is the temperature. Okay. Now what is the advantage of this gas thermometer? Instead of taking this much gas into this cylinder, if I take another quantity of gas, another quantity of another gas into another cylinder, I will do the same experiment, I will find the same behavior. Same behavior means this linear behavior. With height. Same temperature behavior, and the height will change linearly with these things. So this is the advantage of gas thermometer. If you take any gas of any amount, you will find this linear behavior of temperature with, I mean, in this setup with height. Actually, this is pressure times volume. Since I have fixed my pressure in this particular apparatus, my pressure is fixed. My volume is H times A, or A is fixed. So I have only one variable H. You will find this linear behavior. And what is the advantage of having this linear behavior? The advantage of having this linear behavior is that if I calibrate the thermometer at 0 and 100, all the thermometer, all this kind of apparatus will give me a universal reading. If I put this apparatus into another object and half of this H has increased, I mean H goes from here to say H here, which is H plus half H. So this H goes to here, H plus half H. Then I can say that the temperature is 50 degrees. And this is true for all thermometers, because this is the properties of line that this is obvious that if I find the temperature here, so this time by this is equal to this by this. Same thing will happen for this triangle. So you know this. So this by this will be equal to this object by this object, and they are same. So the increment, the ratio of increment of height will be same for all these gas elements in this set. Whatever gas molecules we choose, whatever gas we choose, whatever the volume of gas we choose, it doesn't matter. They will be same. So we have some universal instrument. So this is the property of ideal gas. So we have some universal instrument, universal instrument which can be used to calibrate the temperature, which can be used to measure temperatures. So this is the advantage of gas thermometer. So we have some universal apparatus. Now there is another important advantage of having a gas thermometer. As I told you that is, so in order to calibrate a thermometer, you need 2 points. 0 and 100, we have used the melting point and the boiling point of water, and you know that these are these are dependent on the condition while we are doing this experiment, while we are calibrating these thermometers. These are not independent of conditions, surroundings and conditions. So we want to have some more fundamental quantity. I mean, we are dealing with water and ice and steam because we are obsessed with water here. I mean, our surroundings is full of water. But universally, we want to choose some other more fundamental and absolute scale for calibrating this thermometer. And gas thermometer actually gives us an idea. If we extrapolate this line into negative direction, it will found out that it turns out that all these cars will intersect this 0 of this H or 0 of this PV axis at 273.16. So this number has very important physical significance. This number tells you that you cannot go beyond this line, beyond this limit, because going beyond this limit tells you that, I mean, 0 of this axis tells you that the pressure at this temperature, at this point, becomes 0. and by definition you cannot have negative pressure. So this is the absolute lower limit of temperature up to which you can go. You cannot go beyond this, and this comes from this simple experiment. Okay, it has very deep physical meaning, but we are not going to discuss that. Maybe in the statistical mechanics course you will understand what is the physical meaning of that. We are not going to discuss that, but this simple setup gives you the idea that on temperature you have a lower limit. You cannot go below certain temperature. Okay, as in the case of relativity, you know that the speed of any object cannot be arbitrarily high. There is an upper bound. The speed of light is the upper bound, which is not intuitive, right? So you might think that intuitively you can speed up an object into arbitrarily high speed, but it turns out that this is not the case. In this case also, this is not intuitive. I mean, if you extract heat from an object, you should be able to pull it down into arbitrarily low values, but it turns out that this is the important temperature. At this temperature, at this point, beyond this point, you cannot go. So this is the absolute. This zero is not the absolute zero. This is the melting point of melting point of ice. We are obsessed with water, so we started this as a zero. But it turns out that this is the absolute zero, because beyond that you cannot go. So we want to choose a scale where this is my absolute zero. So I have one absolute point. It is universally accepted, universally true. You can go anywhere in the universe. Physics told you that you cannot go beyond this temperature. So you start your scale from this temperature. Next, you need another curve. In order to have a good calibration, in order to have a calibration, you need another curve. Okay, so that point could be the boiling point of ice. That point could be the melting point of ice and boiling point of water. But as I told you that all these points have some arbitrariness, and our objective will be to remove all possible arbitrariness from the definition. The definitions are very important. We want to remove all possible arbitrariness from the definitions, because as when we do an experiment, anybody, anywhere in the universe can do the same experiment and we will get the same result. So that is the objective. In order to get the same result, we need to remove all possible arbitrariness from our definition and from our calculations. So this melting point of ice and boiling point of water, there are some arbitrariness. While you do this experiment, this depends on that. I will come to the discussion of phase transition after thermodynamics, but here I think all of you know about the triple point of water. So there is a unique point for water where there exists. Water can exist in three of its form. It can exist in liquid, solid, and gas state. There is a unique point for that. You should have a unique volume, unique pressure, and at some unique temperature, this will happen. Water can exist in these three phases simultaneously. So that point is called triple point. Okay, so instead of assuming, so our scale will begin from 0. So this is the Kelvin scale. And I need another point to calibrate. So that point will be the triple point of water. So that point I will call 273.16 K. So these are the 2 points. So why we choose the triple point of water? This is because this is a unique point. For a given temperature, for a given pressure and volume and temperature, you can have water existing in three of its possible states: solid, liquid, and vapor. So this is a unique point. In all over the world, all over the universe, one can find out this triple point, this unique point, and assign the temperature, corresponding temperature of the triple point to be 273.6 Kelvin. Now this point is universal, this point is universal, so we have a universally defined scale for temperature. You can divide this region in 273.16 division and have your thermometer. So this is how we can calibrate our thermometer. Any question about the universality and all these things? Okay.
Sir,
Yeah.
so we have not reached this minus 273.16 degrees Celsius temperature. So why we are taking it as uh, our lower bound?
What? So why you are taking minus that zero as the lower bound?
Yes. Why?
Okay. So as I argued that, so I mean, if you do simple experiment with gas thermometer, so you calibrate your gas thermometer at 0 and 100. I mean, melting point of ice and boiling point of water. Calibrate your gas thermometer at these 2 points. Take different kind of gases and different gas thermometer. Okay. So do this experiment. So this is the melting point of ice and this is the boiling point of ice. I have different gas thermometers which are calibrated between these 2 points. And if you extrapolate these thermometers or do some experiment beyond, I mean, below the ice temperature, and you see that all these curves intersect with the x-axis at a given point. This has been observed by experimental. Okay, so this is the experimental curve. You see that all these curves intersect on this x-axis at a given point, and this is your PV axis. So that means that at this point your pressure is zero or your volume is zero,
Volume.
right? So you cannot go beyond that point. That actually tells you that this is the lower limit of your temperature. You cannot go to negative pressure or negative volume. This is the lower limit of your temperature. So that temperature we assign as zero. I mean absolute zero. You cannot go beyond that. So this zero, what is in the centigrade Celsius scale, is the melting point of ice. You can go beyond the melting point of ice. You will have minus temperature. But we find that, I mean, doing this experiment, people find that this zero, beyond this, I mean, something special happens at this point. This is the minimal value what you can obtain. I mean, minimal value of temperature what you can obtain. You cannot go. I mean, you cannot cool down the system more than beyond this point. Something special happened at this point. Your volume pressure becomes zero. So something special happens at this point. So that's why this is considered as the absolute zero. And scale Kelvin scale starts from this absolute zero. And we need another point to calibrate the scale. So that point is the trickle point of water, which is also universal point. Universal thing. I mean, you can only achieve water in its three states simultaneously at a given volume, given pressure, and given temperature. Okay, so that defines your trickle point of water, and that defines my globally accepted or universally accepted scale for temperature. So, any confusion?
Sir, thank you.
But you understand, right? So, what is the what I am going to? I mean, what I am trying to say?
Yes, sir, I got it.
Okay. So, this is the philosophy behind, the philosophy and mechanism behind the gas thermometer. As I told you that you can have any thermodynamic system which are sensitive to temperature can be used as a thermometer. I mean, anything which is sensitive to temperature can be used as a thermometer. So you can have resistance as thermometer because you know that the resistance changes with temperature. So you have this kind of a relation. I mean, resistance at temperature T can be written as R0 1 plus. So you take a particular resistance, you measure the resistance at different temperatures. So R0, A, B, these are some arbitrary coefficient. For a given material of resistance, you can do some experiment. Actually, you need to do 3 experiments that measure the resistance at 3 different temperatures to find out what is the value of R0, A and B for that particular resistance, and then you can use that resistance to measure other temperatures. Okay, so these are the 3 arbitrary coefficients which you need to find out for this given particular material. So this is called, I mean, there are other different kind of thermometers you can use. So in this book, actually, you have this idea of gas thermometer, resistance thermometer, and thermocouple. So have you studied thermocouple? Has it been done in your in any of your courses? Do you know what is a thermocouple? Can
We did
anyone?
an
Huh?
experimental course. Like in an experiment, we
So you
put
have
in
idea, right? You have idea what is a thermocouple. So you can, I mean, you can go to this Dimonsky book and you will understand. I mean, the similar kind of relation. The induced electromagnetic potential, as you know that thermocouple, the induced EMF is depends on the temperature difference between these two junctions, right? So obviously it's sensitive to temperature, so it can be used as a thermometer. So these are different. I mean, anything different. So the importance of gas thermometer I have introduced, and why gas is important, and what we understand from gas thermometer, how to calibrate the scales of the temperature. All these things I have discussed. Now, so temperature. So idea about temperature is clear, right? And why we need to define temperature in a certain way, why certain thermometers, certain material are good for making thermometer, why certain materials are not good for making thermometers. This kind of ideas you should be, I mean, you should have a clear idea about this kind of things. Now, let us come to the quantity called heat. So, this course will be all about heat and temperature. So temperature I have discussed. Now let us discuss. I mean, you all know what is heat, but let us formally discuss. I mean, let us try to quantify few objects. How to quantify heat and what is. I mean, we have already quantified temperatures. In the temperature, now we will quantify what is heat and how to quantify it. So what is heat? Let us assume that you have a bucket of water. This is a bucket of water, and you place this bucket on a hot surface. It could be anything. It could be a hot metal, a stove, whatever. You put this bucket on a hot surface. So what you see? You see that the temperature of this bucket is increasing. Okay, so this is what you see. The temperature of this water inside this bucket is increasing. The water is getting warmer and warmer. So what people thought is that something is going from this hot surface to this water. Okay, some quantity, something is going from this hot surface to this water, which is, I mean, which is abundant in the hot surface and less in the cold object, abundant in hot object and less in the cold object. Some kind of that things is going from here to here. That is, I mean, people call that as caloric fluid. So this is not a fluid. Obviously, you know that heat is not a fluid. It is some kind of energy transfer. But I am talking about how all these ideas have came. So people saw that if we put a bucket of water on a hot surface, the water is getting warmer and warmer. So they postulated that some quantity, some fluid is coming from hot object to cold object, the quantity is abundant in hot object and not abundant in cold object. That quantity is conducting from hot object to cold object. That quantity is called the caloric fluid, and that is equivalent to the heat. Something is going from hot to cold things. So this is the idea of caloric fluid. Now, how we can quantify, how we can measure how much amount of heat is flowing from this hot surface to this cold water. Delta Q, amount of heat, is going from hot surface to this cold water. This is equal to mass of the water times delta T. Let us assume that the amount of increase of temperature of this water is delta T. We already have the notion, have the idea of temperature. We have already defined how to measure temperature, what is temperature. So we can quantify now starting the temperature. So we have quantified the temperature. So now it's possible to measure delta T. Say at a given instant of time, the water is at temperature T, and next instant the water is at temperature T plus delta T. So the increase in temperature is delta T. So how much amount of heat, this caloric fluid, we need to increase such a temperature is quantified as delta Q. So delta Q should be proportional to mW and the amount of increase of temperature. So this is how we quantify heat. Okay. So this is the definition of heat. Now if I take this mW, the mass of water in grams, then this amount of heat we call calorie. If this water is in kilogram, then we call this amount of heat as kilocalorie. So can anyone tell me, anyone give me some simple argument why this amount of heat transfer is proportional to the mass of the water? So this is an assumption, right? Actually, this is not an assumption. Why this should be proportional to the mass of the water?
The more the mass we have, the more we have to provide heat, obviously, because to raise the overall temperature of the whole water body, we would need more heat. If you have,
What is your answer?
so if we have, if you have a larger amount of water, and to raise the temperature of the whole water as a whole, then we would need more heat to raise the temperature. Whereas if we had lesser amount
Yeah,
of
so
water,
yeah,
heat.
so
This is intuitively saying.
this is right. Yeah, so this is some, yeah, so this is right. This is the qualitative. So there is a theme called principle of identical object. Have you ever heard that? Okay, so what is principle of identical object? Let us assume that I have two such buckets. Okay, so let us assume that I have one such bucket and I have placed another such bucket here. So these are two identical objects. Same amount of water, everything is same. So how much amount of energy? Let us assume that in order to increase delta T amount of energy for this bucket, I need delta Q amount of heat. So same amount of heat I will require for this object, this bucket, because this is the principle of ideal of identical object. These are two identical objects. A similar amount of heat for this bucket. So together I need 2 delta Q amount of heat to increase the temperature of both these buckets by amount delta T. Okay. So that actually tells you that this should be proportional to the mass of this object. Okay, so this is how we define our unit for heat transfer, unit for heat. So calorie and kilocalorie, the definition is obvious, and this is defined in terms of water. So if you are given any problem with water, then you can easily calculate what is the amount of heat you need to increase certain values of temperature for water. But if I go to another object, let us assume that instead of water, I have a copper. So I have a block of metal. Let us assume that I have a copper block. This is a block of copper, a metal block. I want to increase this temperature by delta T amount. So how much amount of heat I need to increase that? So delta Q will certainly be proportional to, in water case is proportional to the mass of that water. Here also the same principle of identical object will apply, and it will be proportional to the mass of copper. Okay, this will obviously proportional to the amount of increase in temperature delta T, and these two quantities M and delta T, these are universal. Universal in the sense that instead of copper block, if I take an iron block, these two quantities same mass and same temperature, these two quantities will remain same. If I take water, these two quantities will remain same. I can always fix the mass at certain values, so they are not dependent on the properties of this block. So where comes this properties of this block? This copper. So there comes a coefficient C, coefficient of proportionality. We call this the specific heat. Okay, so this is the specific heat. And obviously, as we define the unit of calorie and kilocalorie using water, the specific heat of water, C of H2O, is 1 calorie per gram or 1 kilocalorie per kilocalorie. Right? So this is the definition. This is how we define the specific. For any other object, any other metal, we need to, since we have already defined the specific heat, heat in terms of water, so specific heat of water comes from the definition, this definition. If we can take some any arbitrary object instead of this water, I can take this copper block as defining object for heat. Then the specific heat of this object, this copper will be 1 and water will be different. But this is the universally accepted convention that specific heat of water is this. Now you can try to find out what are the specific heat in this convention. What are the specific heat of other objects? So this is clear. This idea is clear, right? So there is nothing important or nothing serious about this number, 1 kilocalorie per gram or 1 kilocalorie per gram for water specific heat. This is just a consequence of definition, how we define heat, how we define calorie. Okay, so instead of taking this water example, I can start my problem with the example of this copper block, and I will obtain the specific heat of copper as this and the definition of calorie different. You understand the point, right? So there is nothing special in that, but that is the globally accepted convention. Now the question is how we can measure this specific heat for copper. And measuring the specific heat, how will help me to predict future behavior of this substance. So that is the objective of thermodynamics. I will discuss that and end here. So this is the last point of discussion. What we are going to do? We are going to measure. We are going to in this course, in whole of this course, we are going to define different properties, different objects, different functions, and different variables. This is the objective of thermodynamics. We will measure those variables using some experiment, and we will see that measurement and knowledge about those parameters, those variables, those thermodynamic coordinates will give us a power to predict the future evolution of the system. So that will be the whole objective of this course. Okay, so let us give you a simple example. If we have an idea, I mean first, so this is the definition of it. This is why I have defined it. That immediately gives us the specific heat of water is this. Then I have this conclusion that if I take any other metal or any other object, any other thermodynamic system, I want to increase their heat by some delta T amount. I need to follow this relation, and only unknown quantity in this relation is this C. Once I measure this C, once I have some knowledge about this C, about this specific heat, I will be able to calculate whatever amount of heat I need to increase certain amount of temperature for that particular metal. Now C you can calculate. C will depend on the properties of this metal. So this is a copper block. C will depend on the properties of this copper block. If I take an iron block, if I take a lead block, this the value of C will be different. Okay. So you can try to calculate, theoretically calculate the value of this C from your theoretical understanding about the properties of this metal. Okay, so that is a part of statistical mechanics course. While you theoretically calculate what will be the value of C from the number of atoms, volume, area, properties, interaction, etc. So that will be a part of statistical mechanics problem which you will learn in your, I think, in your next semester. But in this semester, we are not interested to calculate C from theoretical calculations. We are interested to measure C from experiment. We can use simple experiment to measure C. And once we have the measured value of C, we have the prediction for this, thermal prediction for this material. So what experiment we can do? So let us assume that I have a bucket of water. Simple. Let us assume that I have some amount of V volume of water at temperature T1. Okay? And let us assume that I have some copper balls which are heated at some temperature T2. So this is my simple apparatus. I have some water and I have some copper ball which are heated to a different temperature T2. Now what I do, I drop this copper balls into this water, stay for some time so that this copper ball and water reach to an equilibrium. So what will change? The temperature of this object will change. So water volume V and mass M, and the mass of this copper ball, say this is the mass of water M H2O, and this is the mass of M copper. Okay, so the temperature, so T1 is the temperature of water, T2 is the temperature of this hot copper balls, and if I want sufficiently large amount of time so that this copper ball and water come to an equilibrium, they will reach another temperature Tm. So you can have a simple diagram like this. So you have T2 temperature copper balls, you have T1 temperature water, and in equilibrium their temperature is Tf. So this is the situation. Now we do another postulate of thermodynamics. So what is the postulate? The postulate is that summation over delta Q is equal to 0. So when I drop the copper balls into this water, there is a change of delta Q in the copper ball, there is a change of delta Q in this water bottle, right? So there is a change, okay, so this postulate, so this is the postulate. So delta Q of H2O plus delta Q of copper should be equal to 0. Now what is delta Q of H2O? So delta Q of H2O is nothing but the mass of water specific heat of water. So specific heat of water is 1 and delta T of water. So what is the delta T of water? Water was at T1 is goes to Ts, so Tf minus T plus, so delta Q of copper will be mass of copper plus the specific heat of copper plus Tf minus T2 is equal to 0. So from here actually all these quantities are known. Mass of water is measurable, you can measure. Mass of copper is measurable. T1, T2 and Tf, this can be measured by your thermometer. So you can calculate C. C will be your MH2O by MCU, Tf minus T1 divided by Tf minus T2. So doing this simple experiment, you can measure what is this heat capacity. And once you have measured what is the specific heat for this copper, then you can know, you can measure how much amount of heat you need to increase certain amount of temperature of that copper block. I mean, you know the thermal behavior of that. Okay, so these kind of things we are going to do in this course. So today actually I have discussed about the chapter 1 of your Zimonsky, and I have also discussed something about chapter 2, some parts of chapter 2 of Zimonsky. Okay. So so you read, your objective will be to read chapter 1 and chapter 2 of Zimonsky. Chapter 2, there are some mathematical things which I have not discussed, some partial derivatives and something like that, which I have not discussed. So next class I will discuss that. But it is important that, I mean, this kind of partial derivation, some mathematical tools will be very, very useful in this course. So better you start doing all these things. So do you have any course on mathematical physics? I do not know. I mean, do you had any course on mathematical?
We are currently having one, sir.
Huh?
Yes, sir.
You had a course on mathematical physics?
Yes, sir, we have one. We are doing it right.
You are doing it
So
now?
we are doing it, sir. In this semester, we are. Yes,
so partial differentiation and different relation between partial differentials, this kind of things has been done in that course already, or it will be done?
No, sir, not yet, sir. It will be done.
Okay, so I will give a very brief introduction about those things, but I mean, those things are important. So your objective will be to study carefully chapter 1 and chapter 2 of Zimonsky. Some part of chapter 2 I have covered, but there are other parts which I have not covered, that I will do in the next class. Okay, so anyone have any questions or confusions? I mean, as I told you that you are free to interact me in between the class, okay? Because since we cannot, I mean, I cannot see you, you cannot see me personally, so it's very difficult, and sometimes it becomes monotonous for you and me both. So more interaction will be appreciated. Okay, from the next class, I will try to ask more questions so that we can have more interaction. Okay, so if there is no question, then let us end this class. And if you have more questions, some questions after this class, you can always send me email, then I can address those questions in the next class, or you can ask in the beginning of the next class. So, but I want more interaction, okay, because otherwise, this will become very boring and monotonous. Anyone want to say anything? Okay, so let's end this class here. From the next class, I expect to have more interactions, more questions, and more discussion on these topics. These are very simple things. Okay, you understand that thermodynamics is an empirical subject. This is a very simple subject, but this will give you some very important conception about the development of any kind of theory. This is a classical subject. Thermodynamics is a classical subject. very old. I mean, it has started developing from 16th century. Then it keeps on developing. Now also it is developing. So this is a very old ancient subject, but this gives you very good conception that how you can do some simple experiment or do any kind of experiment and draw some prediction from those experiments. So this is what you will learn in this. So this is not very mathematical. I mean, mathematical things are, it's not very much mathematical. You need to know some differential calculus, but apart from that, you do not need to know. I mean, these do not involve any big mathematical calculations or something like that. But this is a very classical conceptual subject. So you should carefully read these topics. Okay, so let us end this discussion here. If you do not have any questions, yeah. So I think you do not have any questions. So see you in the next Sunday class.
क्लास खत्म भाई लोग